Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of car insurance cold calls. Um, and at the end here, we have a column called car insurance. And if we look at the feature descriptions, we'll see that car insurance is basically asking if the client subscribed or not. So essentially, was the cold call successful or not? And we're going to try to predict the success of the cold call based on the other features. So let's hop into the notebook. I'm going to be using NumPy and pandas for working with the data, and then for pre-processing we'll just use the train test split function and standard scalar from sklearn. We'll use a whole bunch of classifiers today and see which one works best. Let's go ahead and import all of that, and we can load in the data using pandas.readcsv. Now, I'm just going to grab the train set. I'm not going to worry about both of them today. So I'm going to paste in the file path from the train CSV and then check out how it looks. I'll zoom in a little. And you can see we have a good number of object columns in here that we're going to have to encode, as well as some missing values that I'm seeing right off the bat. So let's get a little closer look at what's going on with data.info. And you can see we do have a few columns with missing values and 8 object columns in total. So let us begin pre-processing. Alright, so I'm going to create a function called preprocess inputs that's going to take in a data frame, and for now all it will do is make a copy of the data frame and return it. And now we can store the processed version of data in X. So right now X is just a copy, but now as we add things to our function, we can see the result down here. So the first thing to do is probably drop some columns. So only one column I see right away, which is ID. This column is not useful to us because it's just a unique identifier for each example, and there's no way to draw similarities between training examples using this, since there's a maximum number of unique values in it. So let's go ahead and drop the ID column with df.drop ID axis 1. Alright, it's gone. Now I guess we should look at the missing values. So the isNA matrix we get with x.isNA will have a true wherever there's a missing value and a false otherwise. We can then sum this over the row axis to get the total number of trues in each column, total number of missing values in each column. So this looks reasonable. This one's a little troublesome maybe. We can get a better idea of how big these numbers are by instead taking the mean, which will add up all the trues and then divide by the length of each column. So we'll get a percentage of missing values in each column. And you can see 76% of the values are missing in the outcome column, so we're not going to use that column. It's just too many missing values to fill. If we look at what outcome means, it's outcome of previous marketing campaigns. So many, 76% of them did not have a previous campaign. So we're just going to drop this column. Let's do it up here. Alright. The rest of them are fairly okay. We have 0.4% missing here, 4.2% missing here, and then here is a little high, 22.5, but I think it's just in that, just making the cut. We'll fill these columns since they're all categorical columns: job, education, and communication. See, they all have categorical values. So we'll fill them with the mode of each column. If we take, for example, job, and take the mode is management. So management appears the most. So we'll just plug management in for all the missing values. And we can get the actual string value by indexing at 0. So in our function up here, fill categorical missing values with column modes. And what I'll do is for column in, and I'll include all of them. We have job, education, and communication was the last one. we'll take the column and use fill NA, which will fill any missing values with whatever value we plug in. And we're going to plug in df subcolumn dot mode sub 0, like I did before. And let's set that equal to the new column. So now if we run this, and we take a look at the isNA matrix, the means are all 0. If we sum this over the rows and then again over the columns, we'll get the total number of missing values. So there are no more missing values in our data set. Alright, so now that missing values are taken care of, we should probably start encoding the categorical variables. So we have a few here, and we can get a good sense of the variables by taking a look at how many unique values we have in each one. So I'll create a dictionary that's going to map the column name to the length of unique values in the column. So I'm going to take x subcolumn, take the unique values, and then take the length. And I'm going to do that for every column in x.columns. So this is actually returning it for all the variables, including the numeric ones. And it's not as important to know this about, for example, how many days passed. We don't need to know how many unique values there are. So all I'm going to do is do x.select dtypes object dot columns. And that will just get the columns for the object columns, string columns. Alright, and we can see we have very reasonable low numbers here. These two are the only ones with a high number of unique values, and that's because they're time values. So these are actually numeric, but just encoded as a string. So there's a few ways we could go about this. We could extract out the different hour, minute, second features and put them in their own columns. But I think we don't really need all that information. What would be more concise and probably better for the model is if we just calculate the duration between the start of the call and the end of the call and include that on as a single feature, how long the call was, maybe in seconds. So we can do this like so. If we take the call start column, let's note if I grab a single one of these strings and I call pandas.toDateTime on the string, it will turn it into a datetime object. And what's great about this is if I do it again, let's say I do it like this. If I do it for another datetime, let's put this one first, and I subtract, we can calculate the difference between two datetime objects. And it'll actually tell us how many days, hours, minutes, and seconds the call was, simply by a subtraction operator. And then once that's done, we can take this new quantity and apply, well actually we can just get .seconds of it, and it'll give us the number of seconds in as an integer that the call was. So I want to turn, I'm going to create a new column that contains the call end minus the call start, and then take the seconds. So I'd also like to point out that we can, instead of just passing strings in here, we can pass in whole columns. So we'll put in call end, and in here we'll put x sub call start. And you can see for each value we have the duration of the call. So if we apply a lambda function now, for every x we turn x into x.seconds, we'll get the number of seconds that each call took. So let's use this in our function. Let's encode time, I'll say duration feature. Maybe extract duration feature. Alright, so we're going to call this one duration. Maybe call duration. And that's going to be this thing. I just have to change the x's into df. And I believe that's all we need to do. If we return this now, we should have a duration at the end here that contains the difference between call end and call start. So now that we have this, we don't need these two anymore. So let's go and drop them up here. df equals df.drop call end, or call start, and call end. then we're dropping from axis 1. Okay. So that took care of the times, and now we're left with a few more. So let's look at this now. These are the remaining categoricals. Now, we notice one of them has 2 values, and so that we immediately know we should binary encode. Because when a column has 2 values, it doesn't matter if there's an order between the values, because you'll encode them in the same way. You just send one of the values to 0 and send the other to 1. So let's do the binary encoding. And we'll take the column, I believe it was communication, and we'll call .replace on the column. So .replace allows us to pass in a dictionary that contains a mapping for the elements of the column. So we know we only have 2 elements, that's telephone and cellular. So we can just map telephone to 0 and cellular to 1, and that's all we have to do. This will perform the replacement for every single value in the communication column. So let's set that to the new column and then take a look. Communication is now 0s and 1s instead of telephone and cellular. Alright, so we run this now. We just have 4 remaining. We have job, marital, education, and last contact month. Now we know none of these have 2 values. They all have 3 or more. So now we have to pay attention to the ordering, if there's an ordering of the values, because we will encode them differently if there's an ordering. For example, if there's no ordering between the values, and we just set them equal to integers like this, the model will automatically assume that there's some sort of meaning behind that ordering. It'll say a high value of job is greater than a low value of job. And if there's no true ordering between the values in job, then we'll confuse the model and we'll lose out on some information. So we've got to be careful which of these columns are ordered and which are not. So job is definitely not. There's no way to order between jobs like this. Marital as well, not really able to order between these. Education, however, we can, because primary, secondary, tertiary, there are 3 in here. They do go in a certain order. And it is a measure of how much education. So we will encode this as an ordinal feature. So I want to look at the last one here, last contact month. This would also be an ordinal feature, and that's more self-explanatory. I mean, just because the months do go in a progression. So let's do our ordinal encoding. And for ordinal encoding, we can also use the replace function. What we'll do is take, which was it, education, and call .replace, and we'll pass in a dictionary with a mapping. We have primary, which we'll send to 0, secondary, which we'll send to 1, and tertiary, which we'll send to 2. And let's store that in the original column, and that should have done it. If we look now, education is now 0s, 1s, and 2s instead of strings. And the last one to do is the contact month. So let's just do a similar thing here. So I'll change this to last contact month. And the mapping here is going to be all the days of the month with integers assigned to them. So let me just paste it in to save time. We have January all the way through December, 0 through 11 as the integers. So as long as the ordering is intact, this should work. Yeah, and you'll see last contact month is now as integers, and education is as integers. The final 2 remaining are job and marital. And there's no ordering between these, so we're going to use one-hot encoding. Pandas.getDummies will do that for us. We pass in the column we'd like, let's say job, and it will send each unique job to its own column, and we'll have a 1, which will correspond to the original value of that example. So you see that we have a 1 for management, for example 0. That's because we have management in the job column, for example 0. and the ones will match up to the original examples. So we can also include a prefix here. Let's call it job as well. And that will just put job at the beginning of each column name so that we know where these columns are originally coming from. So I'd like to create a function up here called a one-hot encode. It's going to take in a data frame and a column that we'd like to encode. First thing we'll do is create a copy of the data frame so we're not modifying the old one in place. And then once we do the encoding, we will return the same data frame. So we want to create these dummies with pandas.getDummies for whatever column we pass in. And we'll include the prefix to be the same as the column name for now. Then we're going to concatenate together with pandas.concat the original dummy data frame and the new dummy columns side by side, so axis 1. And then once we've concatenated them together, we can drop with df.drop the original column from which we created the dummies. So let's go ahead and run that function, and then we can call it down here in our one-hot encoding. So all we have to do, we should do for each column. So for column in, and the columns we're encoding here are job and marital. So what we'll do is set one-hot encode equal to df, and we pass in df and whatever column we're iterating through. So if we run this, you should see we now have our dummy columns on the end. We can no longer see all the columns, but we can ensure that there are no more object columns by checking here, and sure enough, everything is numeric now. So the dataset is fully numeric, no missing values. The last thing to do is to scale the data. So for scaling, we want to scale to give each column a similar range of values. Right now, the range that each value takes is very different, and so scaling is a method of standardizing them or compressing them into some range so that they all take a similar range of values. So we're going to use a standard scaler, which will give a shift and a scale to each column, so that each column has a mean of 0 and a variance of 1. And before we do the scale, we do have to split the data frame. So I'm going to split df into x and y, where y is going to be what we're trying to predict. In this case, it's the car insurance column. That was the flag that we're trying to predict here. And x is all the rest of the data. So df.drop car insurance from axis 1. And once we have split into x and y, we can do our train test split. Train test split will give 70% of the data to the train set and 30% to the test set. Well, you can choose how much you want to send to the train set. That will return 4 new sets of the data when we're done. We'll split x and y into xtrain, xtest, ytrain, and ytest. Using the train test split function from sklearn, we pass in x and y, specify a train size. I'll do 70%. And this does also shuffle the data for us. So before it makes the split, it will shuffle the data in a random way. And because it's random, I'd like to include a random state so that we can always reproduce the results of the notebook. Alright, and once we have those 4 sets of the data, we can create our scaler, which is a standard scaler from sklearn. And this is, like I said, it will give each column a mean of 0 and a variance of 1. We'll then fit the scaler just to the train set, because we sort of want to pretend we don't have access to the test set at the time of pre-processing. And then we'll transform both the train and test sets using scalar.transform, like so. However, scalar.transform does return a numpy array, so we lose the column names and the indices if we do it this way. I just want to keep it as a data frame so it's nicer to look at and easier to work with if we want to. So I'm going to turn it back into a data frame afterwards, keeping the indices as they were. and the columns names as they were. Alright, and I'll do the same thing for xtest. Just replace all these with xtest. Alright, and once we've scaled, we can now return these 4 sets of the data instead of just df, and take a look at xtrain. So here's xtrain. It has been scaled. If we look at the mean of each column, you can see they're all very close to 0. And if we look at the variance, they're all very close to 1. Okay, so I think we're done with pre-processing. Now we can start training the model. So ytrain is the classification flag for our car insurance. 1 means the cold call was successful, 0 means it was not. And what I'm going to do is create a bunch of models. I'm going to train a whole bunch of different models here. I'm going to create a dictionary containing each of the models that I imported at the top. So we have quite a few. And for the sake of time, I'll just copy this in. So we have logistic regression, k-nearest neighbors, a decision tree, 2 support vector machines, one with a linear kernel, one with a nonlinear kernel. Then we have a neural network. Then we have our 2 ensemble methods, which is random forest and gradient boosting. So we will iterate through this dictionary, getting the name and model. We can call models.items. Items will return the key value pairs as tuples, so that we can iterate like this. And we'll fit each model as we go on the train set. And once we fit it, we'll just print out a little confirmation message that says the model was trained. And you can see they are training. And they have finished. So last thing I want to do now is see how they performed. So for each name and model, in models.items, like before, we're going to print out the name of the model, followed by the accuracy value that we're getting. Oh, this should be a string. We're gonna print out the accuracy value evaluated on the test set. So I'm displaying it to 2 decimal places with the % sign, and formatting that with model.score. So the score function will return the accuracy value if it's a classification model, and we pass in the test set to see how it did. And I'll just multiply this by 100 so we get it as a percentage, and take a look. Alright, and it looks like, in this case, our ensemble methods are really beating the rest of the pack. So all of our single models did fairly similar. K-nearest neighbors did the worst. All the others did very similar, 77 to 79%. Neural network with the highest. But our random forest and gradient boosting really did make a difference. Gradient boosting is winning with an 83% accuracy. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content. And leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.